Hey guys, hope everybody's doing well. This lesson here is going to be a three-parter for scientific notation. So you'll watch part of it and then you'll take a break and you'll solve some scientific notation problems and then continue from there. You're going to want to go get your notes from your Teams page before I start this. If you can print them, we're going to be filling it out as we go. If you can't print them, then add this to your notebook. And you may need to go back and fill some things in. These notes are going to be super important for everything we do because there's going to be examples for a lot of it. So let's go ahead and share screen here so we can go ahead and get started with scientific notation. So the first thing is what is scientific notation? So if we're looking at our notes here, and again, these are already for you on your Teams page. You only need to write these down if you can't print them. Scientific notation is a way of writing really big numbers or really small numbers. So this is going to be things that occur in space, the weight of really large objects, or if we're talking about small things, you know, maybe the pixel on a TV screen or the thickness of a piece of hair. Those are really tiny things. So it's a way for us to write really big numbers or really small numbers. And here's the rule for scientific notation. How do we know if something is in scientific notation? Well, we're going to move the decimal point. And we're going to make sure that we're going to write it as a number that's between 1 and less than 10. So it has to be larger than 1 or equal to 1, but it has to be smaller than 10. That basically means it's going to be a one-digit number with a decimal point afterwards. So 1.8. 6.7, you know, 3.254. There's always going to be that one digit and then the decimal point, and then it's going to be multiplied by some power of 10 because a power of 10 is every time we move an exponent. The opposite of it is standard notation. Now this is what we already know. This is what we work with. This is just regular numbers. A regular number written with no exponents. 4,800,000. That's standard notation, okay? Now, in order to have these two things work together, what we're going to say is that really big numbers, the billions, the trillions, those have positive exponents. The small, tiny little decimals will be the ones that have negative exponents. We talked in the previous section about positive exponents, negative exponents. If you remember, negative exponent flipped it to the bottom of a fraction. Well, a fraction is a small little number. So the negative exponents work with our decimals. So again, you can print these notes. If you can't print them, then pause the video now and copy these down. So let's look at our examples for what scientific notation is going to look like. How do we write a number in scientific notation? Well, these are two really large numbers. The first one is 45, and this would be millions, so that's 45 billion. And this is 12,300,000. Really big numbers. Well, to be in scientific notation, I need to take the decimal point. And so in this number, the decimal point starts at the end. And I need to move it all the way to in between the 4 and the 5. That's going to give me a number that's larger than 1, but less than 10. It's going to be 4.5. Well, I'm going to move the decimal. And I like to create a visual. So I'm going to move it all the way from here to there. So this is going to become 4.5 times 10 to the, and we're going to figure out what power it is. So I move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So that becomes times 10 to the 10th power. So the decimal starts here at the end, and then I have to move it all the way to between the 4 and the 5. And then I have all of my loops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's the exponent. So that's writing a number in scientific notation. All right, so let's look at a second example of a bigger number. So I have my decimal at the end. I want you to think about where it needs to end up and finish. It's going to have to go all the way here in between the 1 and the 2. So it's going to move 1, 2, 3, 4, 5, 6, 7 times. Well, this becomes 1.23 times 10 to the 7th power because the decimal moved 7 times. I want you to notice on both of these examples, all of these extra zeros at the end, all of the extra zeros at the end are left off the final answer. I'm taking something that's really large and I'm just rewriting it with something that's smaller and easier to work with. All of these zeros are not included in the final answer for scientific notation. Okay, so let's go ahead then. I want you to try this example. So take a moment and write this down and put it in scientific notation. All right, hopefully you're back after pausing. I'm going to go ahead and show it to you here. The decimal is at the end, and I need to move it all the way between the 3 and the 7. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. So 3.75 times 10 to the 8th power. Notice all of these were really large numbers, and they all finished with positive exponents. So let's take a look at what happens when we have small little numbers. So here I have little itty bitty decimals. The decimal is all the way here on the left, but I have to move it to be in between the 4 and the 5, because again, I need one digit that's to the left of the decimal. So this one is going to become 4.5 after I move the decimal, times 10 to the, and let's see, I'm going to move it 1, 2, 3, 4, 5, 6, 7 times. Now, because this was a small little decimal, it's going to be a negative exponent because I moved the decimal the other direction. Notice, in the big numbers, the decimal moved to the left. Big numbers, positive exponent. This time I'm moving it backwards to the right. Little decimals, negative exponent. So here's another one. I'm going to have to move it over here between the 2 and the 3. 1, 2, 3, 4, 5, 6. 2.3 times 10 to the, you got it, negative 6th power. All right, let's move up the camera here a little bit. So I want you to try another example. 0.0000704. I want you to pause it and put that in scientific notation. Now that we're back, let's go ahead and take a look. This decimal is going to move all the way over here next to the 7 and between the 7 and the 0. Now this 0 is not one of the ones at the beginning, and it's not at the end. It's stuck in the middle, so we're going to have to include it. So it's going to move backwards 1, 2, 3, 4, 5, 6 times. So this is 7.04 times 10 to the negative 6th power. Now let's take a look at what happens with numbers that are almost in scientific notation. These both look like they're almost in scientific notation, but they're not quite. Yes, I have times 10 to the 6th power, but 142.5 is bigger than 10, so it's not in scientific notation. This decimal is in the wrong place. It needs to be between the 1 and the 4. So I have to move it 1, 2 more times. So this becomes 1.425 times 10 to the, and I'll leave it for a moment, that exponent has to change. It was a 6. This was a number that was bigger than 10, so the exponent has to get bigger. Think about that for a moment. Bigger than 10, exponent gets bigger. I moved it 2 times, so the exponent's going to go from a 6 to an 8 because it has to get bigger by 2 times. This number is smaller than 1, so the decimal has to move backwards 1 time to make it 3.4 times 10 to the, it was -6. The number was smaller, so it has to get smaller. Well, I moved it 1 time, so what is one number smaller than -6? It's going to be -7. Okay, so these are numbers that are going to be almost in scientific notation, but I have to move them just a little bit. So for your IXL assignment, this here is going to be 8G number 1. So this section is based on 8G number 1. Let's go ahead and take a look at taking numbers that are in scientific notation and putting them back. All right, this is also going to be part of your IXL. This one is a negative exponent. Negative exponent means tiny little decimals. So in order to turn this into a decimal, I have to move it back to where it started. Well, I'm going to count this out 5 times. So again, the visual, I think, helped. I'm going to move it 1, 2, 3, 4, 5. And I'm going to put a decimal out there. Well, what am I going to do with all of these loops? Well, I'm going to fill them with zeros. So 1, 2, 3, 4 zeros in front. And think about it. The exponent was a -5. So it took me 1 space to get around the 2. And then I need to put 4 zeros back in front. So this is decimal point 0, 0, 0, 0, 2, 5, 5. And then typically we're going to see a 0 in front of it. It's just holding a place. Let's look at another example. This is a positive 8. Positive exponents in scientific notation means big, giant numbers. Well, which way will I move this decimal to make it a big, giant number? Well, up here, I moved it to put zeros in front because that makes a tiny little decimal. With a big, giant number, I need to put the zeros at the end. So this one is going to move 1, 2, 3, 4, 5, 6, 7, 8 times. Well, what am I going to do with all of these loops? I'm going to fill them with zeros. So it's going to become 3, 0, 4, 5, and then 5 zeros afterwards. Now, why 5 zeros, you might ask? I had to move it 8 times total. The decimal had to move 8 places. Well, 3 of the places are right here. 1, 2, 3. And then 4, 5, 6, 7, 8. I'm going to plug zeros in to get me up to 8 places total. Now, pause the video and try these 2 examples. Now that we are back, let's take a look at these 2 examples that you tried on your own. Negative exponent means small little number. So I'm going to move it 4 times and put zeros in front. 3 zeros in front because one of the place values was to get around the 9. So this is decimal point 0, 0, 0, 9, 1, 9. And the second example was a positive exponent, so that makes a big number. Well, 5 doesn't have a decimal, so I'm just going to put it there at the end. and then I'm going to move it 4 times. So this becomes 5 followed by 4 zeros because I have to move it 1, 2, 3, 4 times. Again, this is IXL 8G number 1. So 8G number 1 is going to be scientific notation and standard notation, and writing the number in the correct notation based on what you see. If you wanted to pause right now and do 8G1, that would be a pretty good idea. I'm going to continue. The other thing we're going to have to do is compare numbers. Which number is bigger? Which number is larger? Well, the first thing you're going to want to do is make sure that they're either both normal numbers in standard notation. That's really easy to tell which one's bigger. Or make sure they're both in scientific notation. Now, if they're both in scientific notation, the bigger the exponent, the bigger the number. That's pretty straightforward. If the exponents match, and I apologize for the spelling error in your notes. Should have caught that first. If the exponents match, then look to the base number to see which one's bigger. So if I go to these two numbers here, 4 times 10 to the 7th or 4 times 10 to the 5th. Well, this one has the bigger exponent, so it's automatically the bigger number. The bigger the exponent, the bigger the number. Now be careful with negative exponents because that's going to be different. Well, in this example, the exponents match. 10 to the 5th, 10 to the 5th. So they're going to have the same number of places. I just have to now figure out which one's bigger. Well, is 3.7 bigger or is 4.2 bigger? Because the exponents match, I now go to the 4.2, and 4.2 is bigger than 3.7, so that's larger. With negative exponents, we have to remember that bigger means closer to 0, because when things are negative, we have to think about what's closer to 0. So which exponent is bigger? Is -5 bigger or is -7 bigger? Well, remember, with negatives, I need the closer to 0. -5 is closer to 0, so therefore it is the one that's bigger. Now, in order to compare numbers, they're both going to have to be in scientific notation. So if I have 4.5 times 10 to the 5th, or 87,400, if I have to decide which one of these is bigger, I have to make them both standard or both scientific. Now, I think both scientific is probably going to be easier. Well, this one's already in scientific, but this one's not. So I'm going to have to take this decimal and I'm going to have to move it 1, 2, 3, 4 times. So this becomes 8.74 times 10 to the 4th. Well, which one of these is now bigger? 10 to the 4th or 10 to the 5th? 10 to the 5th is the bigger exponent, so that's going to be your bigger number. All right. Comparing the numbers, comparing how big they are, is going to be IXL 8G number 2. So this is going to take you through the basics of scientific notation and then comparing numbers that are in scientific notation. If you need to go back and watch this video again, I would highly recommend doing so before you do 8G1 and 2. Stay tuned for your future videos on multiplying, dividing with scientific notation, and adding and subtracting with scientific notation.